Okay, good morning. Let's get started. So, in the last lecture we discussed about discretizing an unstructured mesh that is orthogonal, right? And also we made some comments. Today we are going to look at discretization of of steady diffusion equation on an unstructured and non-orthogonal mesh. Okay, so that is essentially steady diffusion on an unstructured non-orthogonal mesh. Okay, so if we were to draw a typical cell arrangement for a non-orthogonal mesh, let's kind of see how it looks like. So we have a face, okay, and then we have the cells. Okay, the cells are, let's say, more like this. Okay, so essentially we have this is the face F in between. This is my face, and this one is the cell centroid. Let's say this is the C0 cell, and this is the C1 cell. Okay, so we have a 0 cell and we have 1 cell. Of course, we have 2 more cells that are sharing a face with C0 cell, but we are only concentrating on one of the neighbors, right? Once we generate an equation for one neighbor, we can extend it to all other neighbors. Okay, so we have a face F here, whose area normally is in this direction. So this is AF bar, right? And the 2 directions that we have here, one is the one connecting the cell centroid, that is C0 to C1. This we call it as E xi hat, right? That is one particular direction, and the other one is along the face. So this is the other direction, which is E eta hat. Okay. Now, as you can see, these two, do they have an angle of 90 degrees between them? They do not. That means AF bar is not parallel to E xi, right? AF bar is not parallel to E xi. As a result, the angle between E xi and eta is not 90 degrees. Then we can, of course, also define the lengths that are between the cell centroids. Let's say this length we would like to define it as delta xi. Okay. This is delta xi, and we would also like to define this distance between the 2 vertices as delta eta. Okay, so we would like to call this as delta eta. That means delta eta is nothing but the magnitude of the area vector, right? AF bar magnitude is nothing but delta eta. We would also like to name these 2 vertices. This one we would like to call it as vertex A. This one we would like to call it as vertex B. Okay, that basically defines the direction for E eta unit normal. We of course also have the global coordinate system, that is x I hat and y j hat. Okay, so that defines a typical cell with its neighbor in an unstructured non-orthogonal mesh. Okay. All right. So of course the magnitude AF is equal to delta eta. Okay, magnitude of AF bar equals delta eta, and the distance is delta xi between C0 and C1. Fine. All right. Let's move on. Then let's try to integrate our diffusion equation, steady diffusion equation, on this particular cell. Okay, so that is, if I were to write it here, this is basically del dot gamma grad phi plus S phi equals 0. That is our steady diffusion equation. And if we apply finite volume method, we are going to go through all the steps. That is basically integrate this on a C0 cell, then invoke Gauss divergence theorem, convert the volume integral into subspace integral, and then make the surface integral into a summation and so on, and also approximate the source term with the self-centroid value and so on, and then we finally reach this particular equation, that is summation on the faces for gamma grad phi f dot af bar plus s phi bar times delta v naught equals 0, right? That is our discrete equation, right, which is basically the flux balance for the grad phi. Okay. Then of course, what would be our AF bar here? AF bar has two components, right? One is along I cap, the other one is along j cap. Okay, so AF bar can be written as some AX I cap and AY j cap, where AX is actually the vertical distance, right? This would be your AX and this would be your AY. Okay, so remember, AX is not the projection on x-axis. AX is the component of AF bar in the direction of I. Okay, so that means we can write the AF bar as AF bar is I hat AX plus j hat AY, right? That's what we have for AF bar, and of course the gamma grad phi f can be written as gamma f times grad phi, and grad phi can be written as I hat partial phi partial x plus j hat partial phi partial y, okay, on the face f, right, which is shared between C0 and C1 cells. Now, so far so good, but what is the difficulty here? We have these derivatives, that is partial phi partial x and partial phi partial y, which we cannot directly calculate, right? Why is it so? Because the phi values are not stored along x direction or y direction, rather they are stored in an unstructured way, right, all over the place. So that means phi values are only stored at the cell centroids, and these cell centroids do not align themselves along these directions of x and y. Okay, so the difficulty is we cannot work with partial phi partial x partial phi partial y, because phi values are only stored at cell centroids. Okay. As a result, what would be a better way to work with? If we can calculate gradient in the xi direction, right, that is a better way to work with, because xi direction kind of connects C0 and C1, where we have the values, right? But of course, because the mesh is not orthogonal, can I evaluate the gradient as E xi eta partial phi partial xi E eta hat partial phi partial eta? Can I write like this? I cannot write like this, because this is not a orthogonal coordinate system, right? So this is not equal to this, so we cannot work with this. So this is because now the xi eta is not an orthogonal coordinate system, right? So as a result, we cannot write it that decompose into two components of E xi and E eta. Rather, we have to see how the partial derivatives phi x and phi y, these two can be related to the other gradients. Okay, that means we want to look at the relation between partial phi partial x and these two derivatives, that is partial phi partial xi and partial phi partial eta. Okay, in order to do that, we recall that phi, let's say if I want to calculate what is partial phi partial xi, but phi is a function of both x and y, right? I can write this as partial phi partial x times partial x partial xi plus partial phi partial y times partial y partial xi. Can I write like this? Okay. That means if I use a shorthand notation here a little bit, we can write this as phi sub xi, which indicates partial phi partial xi. Okay. So the partial derivative is indicated, represented using a subscript. Then this can be written as phi x xi plus phi y, y xi, right? I can write like this. Similarly, if I want to relate partial phi partial eta, this is phi eta would be what? Phi is again a function of x and y. So I can write this as phi x x eta plus phi y y eta. Can I write like this? Okay. So I am relating the gradients in the local coordinate system, that is xi and eta, to the gradients in the global coordinate system, that is phi x and phi y, right? And of course, together with the grid matrix, those are how does x change with respect to xi, and how does x change with respect to eta, and so on, right? Okay, let's call these equations as 1 and 2. Let's call this as 1, this as equation 2. Now, our motivation is now to calculate what is phi x in terms of phi xi and phi eta. Okay, so we want to get expressions for phi x and phi y, because we want to kind of replace this term and this term with what? With the local coordinate derivatives. That means we want to replace it with partial phi partial xi, partial phi partial eta, and so on, right? And with all the grid matrix and all. So that is the motivation, because partial phi partial xi can be directly calculated. Okay. Now, if it is if we have these two equations, can we calculate what is phi x from these two equations? Okay, of course we can calculate. So let's say we want to get rid of the second term here. We want to get rid of this guy, right? So I can multiply the first equation with y eta, right? And the second equation with y eta, and the first equation with y eta, and second equation with y xi, right? And then subtract them. Essentially, get rid of the second term here. Okay, can we do that? So that is basically first equation times y eta minus second equation times y xi. Okay, and calculate what would be phi x. That will be phi xi y eta minus phi eta y xi equals phi x times x xi y eta minus x eta y xi, and the second term when multiplied with y eta and y xi get cancelled, right? Can we do that? Is it correct? Yeah? Okay, it's correct. Now what about, so this is basically gives us what is phi x, right? This is basically gives us what is phi x. Phi x is phi xi y eta minus phi eta y xi upon x zeta y x xi y eta minus x eta y xi, right? That's what we have for phi of x. Now similarly, can we find an expression for phi y in terms of the local derivatives? To calculate phi y, what should I do? I should multiply the first equation with x eta and the second equation with xi, and then subtract. Okay, so that means I would write first equation times x eta minus second equation times x xi. This would give me, right, phi xi x eta minus phi eta x xi equals, the first terms get cancelled in the 1 and 2 equations, and the second terms remain, that is phi y times y xi x eta minus x xi y eta, right? That means phi y is phi xi x eta minus phi eta x xi upon y xi x eta minus x xi y eta. Is it correct? Y eta. Yeah, it's correct. Okay. So I want to rearrange this a little bit. I want to get the minus from the denominator to the top, because we have in the first equation we have xi y eta, whereas this is kind of reverse. So I would rearrange this and write the numerator as phi eta xi minus phi xi x eta upon, I would rewrite in denominator as xi y eta minus x eta y xi, right? I just took a minus from the top. Then the denominator that we have here, which is basically this expression, x xi y eta minus x eta y xi, which is the denominator in both of the expressions. This is known as Jacobian, okay, this expression. So we would represent this using J, which relates essentially, which is a combination of the derivatives of the x and y with respect to xi and eta, okay, some combination of that. Fine. So far so good. Any mistakes till now? No, they are all fine. Okay. So that means we have now somehow related all of these guys, phi x and phi y, in terms of the phi xi and phi eta. Okay. So we have kind of related them. Now I can go back and substitute these guys into the gamma grad phi, right? This is the original expression, right? This is the expression we wanted to evaluate. So I'm going to substitute for in this gamma grad phi dot AF, right? That's what we want to evaluate. So I'm going to substitute in there these terms. So I think I would need your help to tell me what would be the expression. So we want to calculate gamma grad phi F dot AF bar. AF bar is I hat AX plus J hat AY, okay. So how much this would be? This would be gamma F times I hat partial phi partial x plus j hat partial phi partial y dot I hat ax plus j hat ay, right? This is evaluated at the face and this is also on the face, right? That's what we have. So that means equals gamma f times, we will again get two terms, right? Partial phi partial x and partial phi partial y multiplying ax and ay. So that would be, how much is partial phi partial x? Basically that is this quantity, right? This quantity is partial phi partial x, okay? That means phi xi y eta. So this is phi xi y eta minus phi eta y xi upon Jacobian times ax, right? This is evaluated on the face, plus gamma f times what would be partial phi partial y? That is this quantity, right? That is phi eta xi, phi eta xi minus phi xi x eta upon Jacobian times ay is what we have, right? Is it correct? Any mistakes in here? Okay. Yeah, expressions are correct. Okay. Now we want to kind of rearrange this little bit such that we get the two derivatives separated. Okay, we have these two derivatives phi xi and phi eta. Now I want to collect terms and then write as a multiplication of something times phi xi plus something times phi eta, right? Just like what we do for partial phi partial x and partial phi partial y. Okay, if we were to do that, then what would this be? This would look like gamma f times, if I collect all the coefficients for phi xi, what would that be? Ax y eta minus ay x eta upon Jacobian times partial phi partial xi, right? All on the face, plus what else will be there? So that means we essentially collected this term and this term, right? Because both of them have phi xi as a multiplication factor. What is the next term? Plus gamma f times ay xi minus ax y xi upon Jacobian times partial phi partial eta on the face F. Is this correct? Ay x zeta minus ax y xi, right? This is correct? Ay xi minus ax y xi. Okay? Fine? Okay, so far so good. So essentially we got now our two derivatives, partial phi partial xi and partial phi partial eta with some multiplications in there. Okay? Alright, now we will go back to the schematic that we have drawn about the mesh and see what actually these things are. Okay, so we have Jacobian has all these metrics, right? Xi, y eta and so on. So what is xi? Xi is nothing but partial x partial xi. So what would be partial x partial xi? If you were to calculate, partial x partial xi would be what? So I am calculating what is x value at 1. How do I numerically calculate partial x partial xi? How do you calculate partial phi partial xi? So essentially, what would be partial x partial xi here? x1 minus x0 divided by delta xi, right? Essentially, that would be x1 here, x0 here, divided by delta xi, right? We are essentially relating the derivative of x with respect to xi. That's all, right? Change of x with respect to xi. So that would be how much? x1 minus x0 upon delta xi, right? Okay. What would be? Let me do this one. What would be y xi? Partial y partial xi. If you want to calculate numerically, what would this be? So we have this cell centroid is C1 or 1. The other cell centroid is C0 or 0, right? The coordinates are x0, y0 and x1, y1. We can always calculate what is the derivatives of these coordinates with respect to xi and eta, right? That's all we are doing. Everybody follows? If I were to draw it here, essentially we have these two, right? So the coordinates are x1, y1 and x0, y0, right? And we are going in the direction of E xi and calculating the partial derivatives, right? Fine. So what would be partial y partial xi now? y1 minus y0 upon delta y. So that would be y1 minus y0 upon delta xi. Now we have another direction, which is the eta, right? So what will be x eta? That will be partial x partial eta. We have also identified a name for it. We have these vertices named as B and A, right? So what will be, and eta is along A to B, right? So what will be partial y partial eta or partial x partial eta? xb minus xa upon delta eta, right? Okay, similarly what will be y eta? yb minus ya upon delta eta. Fine. So we have kind of set up all of these things. These are the metrics for all the coordinates. It's quite simple. 0 and 1, A and B, right? So we have these four coordinates from which we are calculating the matrix. Okay. All right. Okay. Now, what about AX? AX would be how much? So AX, we have identified it as the length in the y direction, right? That means the projection of the phase area vector onto the y axis. So what will be AX in terms of B and A values? What will be this height? AX is this one, right? X or Y? YB minus YA, right? Okay, so YB minus YA is my AX. This is YB minus YA. What about AY? XA minus, that is this length, right? That will be how much? XA minus XB, okay? So this is XA minus XB, right? That's what we have. So that means my AF bar is nothing but I hat AX plus J hat AY. This I can rewrite it as I hat times YB minus YA plus J hat times XA minus XB. Okay? Everybody agrees with this? Is the area vectors fine? The notation we have used for the AX and AY. For the AX it is YB minus YA. For the AY it is XA minus XB. Okay? It's not the same. It's B minus A and A minus B. You see that? Okay. Now this will work even if the phase area vector is not inclined like this. Even if it goes this way, it will work, right? Accordingly, XA becomes smaller than XB and AX becomes negative. All that works fine. Yes? Yeah. Hold on. So the question is, what is the partial x partial eta, right? So this is partial x partial eta. So we are talking about the eta direction, that is this guy, right? What are the coordinates we have? So this is the direction. Arrow indicates the direction. It will be, you are talking about x, so it will be xb minus xa upon delta eta, right? xb minus xa upon delta eta. Is that correct? Because it's always this guy minus this guy divided by the distance, right? That's what I have written, right? Okay. Other questions? Area vectors, derivatives is fine? Okay. Fine, so we have all of these guys. Then area vector is also done. Then what about the unit vectors? We don't know what are these unit vectors, right? We only know what is x and y, I and j. The unit vectors will be specific to cells. That means it is specific to phases. Right? Each and every phase will have a local coordinate system, right? Because it's unstructured, right? You may recall if you have a, let's say, a finite difference kind of mesh, then you would probably use one particular transformation which will relate entire your xy into some curvilinear geometry. But here we are talking about an unstructured mesh where each and every cell can be in its own directions, right? So as a result, you will have a local coordinate system for each and every phase, right? So these e xi, e eta are specific to the phase in question, right? And these have to be computed for every cell for all the phases. Okay, so that means what is e xi hat? E xi hat is a unit vector, right? But if you look at that means it's a unit vector that is connecting C0 and C1. We don't know a unit vector, but we know a vector that is connecting C0 and C1. We can certainly normalize that and calculate the unit vector, right? So what is the vector that is connecting C0 and C1 with coordinates x0, y0 and x1, y1? So we have two coordinates x0, y0, x1, y1. What is the vector that is connecting these 2 points? x1 minus x0 I hat plus y1 minus y0 j hat. That is the vector, right? That gives you the total vector. If I want to normalize it, what will be the distance? Divided by delta xi. Delta xi is nothing but again square root of x1 minus x0, which we don't have to write because we have indicated it as delta xi, right? Of course, when you code it up, you have to use square root of x1 minus x0 square and so on, okay? So that is the unit vector. So that means this is, probably better do it slow, okay. So this is basically x1 minus x0 I hat plus j hat times y1 minus y0. This is a vector that is connecting C0 to C1 centroids, right? Of course, the distance would be divided by, if you want to normalize it and find some unit vector, it will be square root of x1 minus x0 and so on, which you would calculate when you write a code. But for now, I would denote this as simply delta xi, okay, to kind of reduce the notation. So this is I hat times x1 minus x0 plus j hat times y1 minus y0 divided by delta xi. Fine. That is your e xi hat. Okay. Everybody agrees with it? We have essentially 2 points. How do you calculate a vector between 2 points? Difference of the x values times I. Okay, fine. What about similarly, can you tell me what would be e eta hat? xb minus xa I hat plus yb minus ya j hat upon delta eta, right? You have chosen b first because your vector is pointing from a to b, that's all, right? That's the only thing, right? Similarly, just like 1 first because it's pointing from 0 to 1, okay? These are all known. Fine, everybody okay with the unit vectors? Similarly, delta eta you would calculate from the magnitude of the phase. AF bar magnitude would give you delta eta, right? When you actually code it up. Yes? IAX plus JAY. But the notation is AX is not the x component of the phase. AX is the component of the phase vector that is in the x direction, in the I direction. Yeah, AX is not the component along x axis. AX is the component along y axis because it will point in the x direction, right? I hat AX is chosen on the y axis as that it points in the I cap direction, right? If you want, I can write it as AYX, but it will be confusing, right? So AX is, so go back to the figure. We have AF bar here, right? This is AF bar. I am projecting this onto two axes, but the axes are not corresponding to the subscripts. Okay, they are interchanged. So the projection on the y axis, I am calling it as AX. The projection on the x axis, I am calling it as AY, because AX would be along I hat, right? And AY would be along J hat. Is that okay? Then AX actually is the length in the y direction, right? And AY is actually length in the x direction. Okay? Fine? No? All right? Magnitude of AX can be less than AY. We don't really bother. Sorry? According to this diagram, length of AX is greater than length of AY. Okay, hold on. So the question is, I think there is some confusion between AX and AY. So AX is, what is AX by definition, what I have drawn, according to what I have drawn? No, on the y-axis. It is on the y-axis, right? This is y-axis, right? It is not along x-axis. It is along y-axis such that it points in the I cap direction, right? So what was, if you go back to our diffusion equation, what was the A east bar? A east bar was how much? Was it delta y times I hat or delta x times I hat? Delta y times I hat, right? You remember? So essentially, I'm using the same notation here. AX is nothing but AX is pointing in the I hat direction, and that is projection along the y-axis, right? You see that? No? Okay, otherwise we'll get back to this after the class. For now, AX and AY have to be interchanged from what you're thinking. Okay? All right. So fine. So we have now have all these metrics that are set up. Okay. So if we go back and evaluate each of these things that we have in terms of the Jacobian and all the coordinates. So let's look at the Jacobian. Okay. So what was the Jacobian given as? X xi y eta minus x eta y xi. Is this correct? Jacobian. X xi y eta minus x eta y xi. Is this correct? Yeah, this is correct. Okay. What is x xi? Yeah, partial x partial xi. We have written it as something, right? x1 minus x0 upon delta xi. And what is y eta? yb minus ya upon delta eta minus x eta will be how much? xb minus xa by delta eta times y xi would be y1 minus y0 by delta xi. Okay. Fine. I just substituted whatever we have calculated for this. Now, we have a multiplication of delta xi delta eta in the denominator, right? And what is the numerator? We have x1 minus x0, yb minus ya. Okay, that is if I go back here, x1 minus x0, that is this quantity, multiplying yb minus ya, that is this quantity. And what is the other one? xb minus xa and y1 minus y0, right? So that is y1 minus y0. Instead of xb minus xa, I have xa minus xb, right? But I can of course change this minus to plus and make this minus and plus, right? Then can I rewrite this as a dot product of these two quantities, this guy and AF bar? Do you see that or no? No? Followed, or shall I repeat again? Okay, let's see it again. So we have, what is the first quantity we have? x1 minus x0 times yb minus ya, right? So that can be thought of as multiplying yb minus ya from here, multiplying x1 minus x0, right? And the second one is xa minus xb times y1 minus y0, right? Of course, there is a delta xi in the denominator, right? So that also can be absorbed into this. So I can write this essentially as AF bar dot E xi by delta eta. Can I do that? Can you check whether this comes back here? Right? We are kind of reducing it to the matrix that we have. Right? Can we write like this? AF dot E xi by delta eta. Because there is a delta xi in the E xi definition, right? So there is this, oh, I'm sorry, there is a delta xi in the E xi definition, right? This also gets absorbed, right? So x1 minus x0 divided by delta xi times yb minus ya would give you AF dot E xi, the ith component, divided by delta eta would remain, right? Can you verify this? Tell me whether it is correct or not. Fine? Yes? Okay. Any mistakes, or is it okay? Fine, okay, reads fine, okay. So Jacobian is done. Then what else we have? We have again the other two quantities, which are basically this one, ax y eta minus ay x eta upon Jacobian. We will come to Jacobian a little later, okay. I will evaluate the numerator here, which is ax y eta ay x eta, okay. So that is how much? Ax y eta minus ay x eta. Is that correct? What I have written, ax y eta? Yeah? So how much would this be? Ax is how much? Ax is how much? Yb minus ya times how much is y eta? Y eta yb minus ya divided by delta eta minus, what do we have? Ay would be how much? Xa minus xb times, what would be x eta? Xb minus xa upon delta eta, okay? Fine? You have to use your notes and see whether this is correct. Ax is the vertical distance, that is yb minus ya. Y eta of course is between a and b, so that is yb minus ya upon delta eta. Similarly, ay is the projection along x axis, that is xa minus xb, and x eta would be in the a to b direction, that is xb minus xa by delta eta, right? Of course, there is some asymmetry here. What we can do is we can just rewrite this by absorbing the minus here, okay? We can rewrite this as yb minus ya whole square plus xa minus xb whole square divided by delta eta, right? What is yb minus ya whole square plus xa minus xb whole square? That is nothing but a dot a, right? Yb minus ya whole square plus xa minus xb whole square delta eta square, right? Same thing essentially. That means I can write this as af bar dot af bar, okay, which is nothing but delta eta square upon delta eta is what we have, right? Upon delta eta is what I have, right? This is essentially nothing but delta eta, because delta eta square upon delta eta, this is the delta eta, right? The entire term, correct? I would leave it there because in the Jacobian also there is a delta eta in the denominator. I want to cancel this delta eta with that one, okay? Because this is the numerator we are talking about, right? This is divided by a Jacobian, and the Jacobian we just had a delta eta here, right? That gets cancelled, so I want to leave it here as it is. So what is the first coefficient now? If I were to complete, the first coefficient for partial phi partial xi is this entire term, right? What is that? That is nothing but ax, the first coefficient is ax y eta minus ay x eta, right? Is that correct? Yeah? Divided by Jacobian. This would be what? This would be af dot af upon delta eta divided by how much was Jacobian? Af dot xi upon delta eta, right? So this is nothing but what? This is nothing but af dot af by af dot xi. Fine. Delta eta gets cancelled. This is what we get. So this is multiplied by partial phi partial xi, right? That's all. Okay, very good. Fine. Everybody is following? Okay. Now we'll do the second term. The second term was how much? That is multiplication of partial phi partial eta. This is ay xi, ay how much? Can you let me write? Ay xi minus axy xi, is it? Yeah? Okay. Divided by Jacobian. We will come to that a little later. So what is ay? Xa minus xb times how much is xi? x1 minus x0 upon delta xi plus how much is ax? Minus, sorry, yeah, it's a minus yb minus ya times how much is yxi? Y1 minus y0 by delta xi, okay. So we got xa minus xb, x1 minus x0, yb minus ya, and y1 minus y0. So if we go back, xa minus xb, x1 minus x0, what would that be a dot product of? Unit vectors, right? Xi and E eta have these things, but there is a plus minus difference, isn't it? So I should take a minus out, because the first one is xb minus xa here, whereas what we got is xa minus xb, right? So if I take a minus out, that would be yb minus ya times y1 minus y0, right? And then plus xb minus xa times x1 minus x0, is that correct? Okay, divided by delta xi, right? So we have b minus a, 1 minus 0, 1 minus 0, multiplying the y coordinates getting multiplied and x coordinates. So this is would be how much? This would be yb minus ya times y1 minus y0, xp minus xa times x1 minus x0 divided by delta eta is what we have. So if you multiply e xi dot e eta, right, and then multiply that with delta eta, I would get this thing, right. So that would be how much? That would be, this would be, I can write this as minus e xi dot e eta times delta eta, right, because one delta xi, one delta eta in the denominator, but this resulting expression has only delta xi, so I would multiply this with delta eta, right. Fine, everybody able to follow? Okay, fine. So, alright, so but what is the total expression we have for the second term? Basically this quantity divided by Jacobian, okay. So that would be, if I put it back, the second one is a y xi minus a x y xi upon Jacobian is what is multiplying partial phi partial eta. So that would be minus e xi e eta times delta eta upon how much was Jacobian? af dot e xi divided by delta eta. So this would be how much? This would be minus delta eta square times e xi dot e eta by af dot e xi. Is that correct? Yeah? Or would the delta eta get cancelled, or it will become square? Square, right? It will go to the numerator, it will become square. I would like to rewrite this thing. Delta eta square is nothing but what? Af dot af. So this I would like to write as minus af dot af upon af dot e xi times e xi dot e eta. Okay? So this is the another expression multiplying partial phi partial eta. Right? Okay. So shall we assemble everything and write our grad gamma grad phi f dot af? We are still there, right? We have still not written the final equation. We are trying to see if we can calculate all these metrics. Okay, so what is our final expression? That would be gamma grad phi f dot af would be essentially this one, right? So that is whatever we got for the first term multiplying the partial phi partial xi, then whatever we got for the second term multiplying the partial phi partial eta, that's what we have, right? So what was the first term? First one is this guy, right? First is this one, right? ax y eta minus ay x eta by Jacobian. What is the second one? Second one is this guy, right? Okay, so can you let me write this? This is basically gamma f times af dot af by af dot e xi, right? Is that the first term? Okay, multiplied by what? Partial phi partial xi f, right? And then we have minus gamma f. Minus is coming from this coefficient, right? Gamma f times af dot af by af dot e xi times e xi dot e eta times what? Partial phi partial eta for the phase. Do you see that? Okay. Now all this is done for one particular phase f, right? This is something like an east phase, right? If we have a structured mesh. Now what do you see? This is something different from what we have been doing till now, right? Till now we only had one derivative coming for every phase, right? If you are talking about east phase, you only got partial phi partial x, right? Or if you are talking about a north phase, you only got partial phi partial y. But even in the context of unstructured orthogonal meshes, we only got one quantity, right? That was partial phi partial xi. But here we get partial phi partial xi component and a partial phi partial eta component. That is a manifestation of the non-orthogonality of the mesh. Okay, because of that you got this one. So that's why you got two terms here. Now let us see, we would like to call these two terms with different names. We call the first one, which is the primary direction, right, which is normal to the phase, which is one direction, is basically called the primary gradient, okay, which is basically partial phi, partial xi. And the second term we have here, which is not the main direction for xi, we call this as secondary gradient. Okay. So we got a primary gradient and a secondary gradient. Okay, so we will kind of make more comments on this, on how to compute these quantities and what is the consequences we get as a result of the non-orthogonality. Now, would the non-orthogonal formulation switch back to an orthogonal formulation if we end up having some cells as orthogonal? Okay, all those things, and finally the discrete equation. All these things we'll see in the next class. Fine. I'm going to stop here. We will start off with this particular equation. Okay. Thank you guys. See you in the next class.